Hello and welcome to another tutorial video for Thinking Particles 7.3 Service Pack 3. I'm your host Edwin Braun, and in this tutorial we'll explore a powerful technique for controlling how fluid interacts with surfaces, just like you saw in the introduction video. Let's unlock new possibilities and take our fluid simulations to the next level. Are you ready? Let's get started. Okay, before we dive into the setup, let's have a look at the scene. The scene is made out of this box we have at an angle, and we have an emitter here where our particles flow down. Let me just play that back so we can see our fluid is dropping down and flowing across the surface. Pretty simple, straightforward setup. Now let's explore how we created and did this setup, and let's dive right into it. Let me bring up the Thinking Particles user interface and let's have a look at the scene setup. In this master dynamic, we can see all our dynamic sets. So that is our whole simulation. And I'll go through step by step what we did here and why we did choose the setup in that specific way. The first dynamic set is our create dynamic set. In this dynamic set, we have an object to particle that brings in our helper object, the point helper. And we just want that point helper so that we can animate the emitter. So that's the only reason we chose a point helper here, to get a position in space that we can animate with max methods. Then we assign to this particle that will be created at the position of the point helper, we assign a scale value. And the only difference here is we scale in the x-axis. So keep that in mind, the x-axis is twice as wide as it's high. The next setup we have in here in the create dynamic set is we use our emitter, and the emitter was created here. That's the group, the particle group we use for our fluid emitter, where we emit our fluid. So we feed in the emitter particle constantly, so that will be called all the time, and we use a flow emitter. And the nice thing about the flow emitter is when we use the rate per area, it will create a constant flow. So whenever a particle has left the emitter, a new one will be created. So we can create a constant flow of particles here. Then we adjust the size and the rates per second, how many particles we want per second, and we'll assign a size to these particles as well. So that's also straightforward, nothing magical or complicated in here. We just define how many particles we want. And as I mentioned already, the great thing is by using the helper, let me just move that away. We can use the helper point just to move around our emitter and animate our emitter. So when I click this, you can see we have an animated emitter point. So that will animate our fluid emitter. Nothing simpler than that. So we have an animated fluid emitter, and we control the amount of fluid with this node. The next dynamic set is our force dynamic set, and in that case we just use force as a gravity. So we grab all the particles we create, including subgroup, that's important. So we have particles and we have sticking particles. And I did that for the tutorial's sake. We don't have to have a subgroup here. That's just totally for visual effects, so to say, or for explaining what's going on. Let's continue. So we have the force and negative force, that's our gravity. And then we go to the next dynamic set. And this dynamic set is our fluid dynamic set, or it's responsible for the fluid simulation. The first entry, and it's important that you keep the order right, because it's a simulation, so we have sometimes dependencies in a fluid simulation, especially when there's collisions or multiple things going on. And we are doing multiple things here. So our order of operators is very important. And as always, the solver should always be the last one in the hierarchy. So that's the last one called. The solver is always on the bottom, and all our flow group, flow boundaries, and everything that's connected to this solver should be above. So very simple. If you know that, all is fine. Just make sure flow group and flow boundary is above the solver. Or if we accidentally move it around, let me just move it down, the boundary would not work anymore because the solver would already have solved the fluid and then the boundary wouldn't work. So we need to make sure that our order is right. We use our SPH solver here, and we have some settings, basic setup for our fluid flow. And here comes something interesting. I'm only using the flow boundary for a kill box. So I have created a kill box, and why would I want that and why would I do that? Let me just unhide the kill box. So as seen from above, that's my kill box. And usually you should have with fluid simulations or simulations that can be pretty complex and finicky, you should have a kill box somewhere so that if particles leak out, you make sure they get killed. Because if particles travel for whatever reason into infinity, you can easily kill your memory and crash 3D Studio Max. So I always feel and think it's a good idea to have a kill box. And creating kill box tests is very simple. You add a flow boundary, select your kill box, and just turn this option on, kill on contact. Nothing else. We have no friction, no boundary, no buoyancy or adhesion or anything. Just kill on contact. That's it. That clears out any stray particles. And the next thing is our flow solver with a subsample of 1. So that's all our fluid simulation. And as I mentioned, we are using the flow solver down here and the particles group with subgroups. So we use all the particles in here to simulate our fluid. The next thing is what we want to achieve. And I don't know if you have noticed in the introduction video, you might want to go back and check it again, or after the tutorial video, you want to check it again. It's a very subtle but fascinating effect. The water flows down this slope, and at some areas it sticks more than on other areas. So it gives you an impression like an oily surface where water suddenly stops and takes some time until it flows around the oil patch or a different surface. Could be any kind of things we want to simulate with our surface here. And we are now going to just define where we want to have stickiness and where we don't want to have stickiness. And I'm doing that with our new MEL programming language we have introduced in 7.1, I think. And now this scripting language we have introduced in thinkingParticles is so powerful. It is fully massive parallel processing the data. It's very fast, and with a few lines of codes you can create all kinds of amazing things. So let me explain this setup. How can we define stickiness on a surface? The first thing we do is we grab our surface. So I'll just grab the node here. And what I want to achieve actually is I want to make sure whenever there's a collision with our object, so when the particles collide with this object, I'm going to do something special. So I'm using a standard U deflector node from thinkingParticles. We are just checking the front side collisions, and I'll have a distance value for when we think it's collided with a surface. The next node is just a standard text map node. And this text map is used, it's a cellular map. This text map is used to define my stickiness on the surface. And right now, this is all arbitrary. So I've decided that white means full stickiness and black means no stickiness. However, you can do whatever you want. You can red, green, any colors, any intensity values, however you want to do it. So those are our inputs into our expression MEL script. And let's have a look now. The script itself has a stickiness slider. So this defines my stickiness. When I turn this down to 0, it's nailed down. It's no movement at all. And the higher I get, the less sticky it will become. So let's have a look at the code and how it works. As I mentioned, it's a pretty straightforward code. We have our inputs that we define. First, we want to have our particles. So we need to know where the particles are from. And the particles is our particles group. Let me just move that a little bit over here. So we can see particles including subgroups. So I have the checkbox for the subgroups as well. So we grab all the particles here. That's our first input. And the one and most important feature you have to learn with this scripting language is the first input defines the massive parallel processing part we are working on. So the first input is our particles, and we will go through all the fluid particles in parallel. So that means we are very efficiently and fast processing our particles, our fluid particles. The next input is our stickiness. That's our control here, the stickiness spinner. Then we create a collision port input that will give us the information of the collision. And the map input, the sticky map input, where we want to know which color value or grayscale value the map has. The next section we have here, also very simple. I'll define some variables I want: position, particle velocity, color, UV coordinates. So let's continue. I use this function collision in detect. So collision in detect means when we have a collision happening. So we see here is our input collision. That's called collision. So we have collision in detect. If you are confused and don't know what functions are available, you just go here with your caret and press the selective help button, and that will bring up your Thinking Particles help manual. And in this help file, you can see all the functions and how they should be used, including samples. So it's very simple and straightforward. We can just copy and paste a sample out into our script and try it out and modify it. So whenever you get stuck or want to analyze or saw a script and want to know what does this function do, just go there, press the selective help button, and you get detailed help about the function. So what we are doing here is we're checking if we have a collision. So if we have a collision, what we do is we get all our important values. So we're getting, for example, the position of our collision. We are getting the velocity at our collision. And we are getting the UV coordinate of our surface where the collision happened. So now we have collected all the information we want from our collision point. And then I'm going to evaluate my texture. And now here's the beauty. This evaluation is totally independent of the actual object. The only thing we care about is the UV coordinate and the map. So we go with the UV coordinate into this map and get the color. The next thing is when this color is above 0.5, let me just bring that over here, it looks better. So if the grayscale value is above medium gray, I'll say, okay, this is sticky. And then I'll apply the position where the collision happened. And I'll modify the velocity of my colliding particle with the stickiness in factor. And then I'll move this collided particle into its own particle group, into the sticking particle group here. Why do I do that? As I mentioned before, I don't have to do that. That's just for illustration purpose, and I'll show you why, so that we can analyze and see what's going on. And if we don't have a white value or medium gray value or greater than medium gray value, we say, okay, you have a free flowing fluid, go ahead, keep on flowing. So we just set the collision position and the velocity that's there. And that's all. Just a few lines of code and we can make our fluid sticky. Very simple, very easy, powerful things. And we can now explore and make this even crazier and more functions. But for now, let's just stick with that setup we have here. And in our last dynamic set, we have our OpenVDB shape. The OpenVDB shape takes care of the surface. So it creates out of the particles a surface. So now let me show how we can do some basic debugging. When we are going here, let me just play back our fluid simulation here. We can see the fluid is running down, coming down here, flowing down, and so on. So we see by default, fluids are set to density. So I see where high pressure and low pressure is. But for our effect, I want to see, is it sticky or not? Is my idea working? So I'll turn off the density view to none so that I only see the particle group colors. And up here, you can see we have the white particles for our fluid and these blue particles for our sticking particles. So now I know when my fluid runs down, wherever I see the blue particles, I hit a sticky spot on my surface. So now let's see what map or how do I control where are the sticky areas on the surface. And that's very simple. As I mentioned here, let me just bring that back. As I mentioned here, we're using the sticky map with a cellular map. Okay, let's have a look in the material editor. And I'm using and opening the good material editor. Just a side note for you guys out there. So we have our cellular map here. And let me just bring the cellular map on our object. Let me just instance that. And let's visualize the cellular map in the viewport. And now it all makes sense. As I mentioned, I just arbitrarily defined white means sticky and gray or black means free-flowing fluid. So now let's have a look. So whenever the particles hit a white area, now the fluid moves over here, it starts to stick. And then it piles up and flows across and slowly moves down. We can also here see how the fluid is sticky or kind of sticky in the white areas and flows very, very slow. Same here again, hits the white spots here and it's sticky. And as I mentioned, this is now a fully procedural effect. So I can change this texture map. I can totally change this texture map and we can have different kinds of stickiness here. So let me just adjust the size maybe the other way. Okay, and let's have a look if this works for us. Let's see. So now we have a lot of sticky areas and some white areas in between where the black areas are. So we could also just reduce the amount of white areas. I think if I just go down, that was the other way around, sorry. We need to go the other way around to have just some splinters here. And as you can see right now, it's so easy, so simple to modify and control. One thing I forgot in my tutorial setup is we are moving right now the sticky particles into the blue group. However, when they become unstuck, we are not moving them back into the white particle group. Just keep that in mind. This is why once they were stuck, they stay blue, these particles. But as I mentioned, that was just for an illustration purpose so that we know what's going on and what we are doing. And this is really showing how powerful this feature and functionality is using MEL and texture maps. This just shows how powerful it is to control the fluid flow on a surface with the help of texture maps. We just feed in the texture map into our MEL, use the UV coordinates, and get the color from the texture map. And we could even use the color directly as a friction value for the fluid if we wanted to do so. We have come to the end of this tutorial. I hope you enjoyed this tutorial and learned some new stuff. Thank you for watching this tutorial, and goodbye.